Good morning, sir.
Good morning, sir.
Yes, good morning everyone. To this potential divider bias. Okay, we understood this self bias configuration properly, and we had solved a numerical, and it was very easy. Okay, now we have gone through that voltage divider biasing. We tried to solve some theoretical part, and after that we tried to solve some numerical, but we were not able to solve that numerically properly. I think we were not able to understand this. Am I correct? Okay, I'll start today's lecture from voltage divider biasing itself. Potential divider biasing. Okay, actually that day we left one point in potential divider biasing that was very important. How to utilize the characteristics, transfer characteristics in finding the particular value of IDQ, IDQ and BGSQ. Okay, this is BG, and here this is BGS, and here this is BDS. This current belongs to IT, this is IS, and this is IG goes to 0. Since IG goes to 0, ID equals to IS. Okay, this is necessary condition. We always try to keep this remember. And this voltage across R2 is VG, and we can calculate VG by this plus VDD into R2 over R1 plus R2. I don't think there is any problem. Now we can apply KVL in this loop, and we can find this equation minus VG plus VGS plus ID into RS equals to 0, and this will provide us VGS equals to VG minus ID into RS. This is equation number 1. Now, this is very important to know about how to find out the value of VGS. So for calculating this value, yes, tell me.
Sir, you have completed till common gate configuration. This topic
Yes, yes, I know. That's what I am repeating it here because we have missed some point. That was very important point. Okay.
Okay.
So that's why I am repeating. Okay. So here, what is that important point? We have to apply two conditions for calculations of VDS, VGSQ and IGS. We have to apply two conditions. First condition, put ID equals to 0. These conditions we have missed on the last one. How to utilize transfer characteristics in calculation of BGSQ and IDQ. So ID equals to, if we put ID equals to 0, then we will calculate VGS equals to VG. Okay. And second point, put BGS equals to 0, and that will lead to provide us ID equals to BG over RS. Okay, so you see, we found 2 point VGS and ID. Okay, so let me draw the transfer characteristics over here. And suppose I'm drawing transfer characteristic. This is the scale for IT. This is scale for VGS. Okay, so see, this is very important point. Here VGS equals to VG and this is positive. So suppose VGS is positive, so this is situated on the right side of this scale and this is VG because this is positive. So it will be situated at the right side. Okay, how to locate the Q point? Problem is how to find the Q point. And these are the transfer characteristics. This is VP and this is IDSS maximum current. So problem is how to locate the Q point. For locating the Q point, we have applied two conditions for locating the Q point. Okay, for locating the Q point, we have applied two conditions. Okay, so first condition, from this first condition, we found that VGS equals to plus VG, and plus VG is situated on this scale at the right side because this is positive. And the second point is VGS over RS. So suppose this point VGS over RS, this is located here, not here, here. This is located here. ID equals to VGS. VG over R. Now we can do one thing. We can take a ruler and we can join these. Can join these 2 points. Okay. Now we have joined these 2 points. So whenever we join these 2 points, and this straight line intersects the transfer characteristic curve at the perpendicular axis and perpendicular or horizontal axis. So this point will be VGSQ and this point will be IDQ. So this is the graphical method to calculate the value of current, drain current and gate to source voltage on Q point. And finally, we have calculated the value. We can graphically mention this only value and this value. So once we found this value ID and VGSQ, we can apply 1 kVL at output loop, that will be plus minus VDD plus IDRD plus BDS plus IDRS equals to 0. This is equation number 2. We can put that value of ID, this value, whatever we have called using graphical method, ID and VDS, this VDD, and we can calculate this value of VD, just value of VDS. Okay, let me solve a numerical problem that will be very easy to understand. So the question is, determine IDQ, BGSQ, BDBS, VDS, VG, BDBS, VGS, and BDC. Okay, so we had not solved any numerical on the last time. This is plus 16 volt, and this is giving like 2.4 kilo ohm. This is 2.1 mega ohm. This is 270 ohm, and this is 1.5 kilo ohm, and you have given IDSS 8 milliampere and VP equals to minus 4 volt. Fine. So directly we start solving this numerical problem. The problem is that we have to calculate the value of Vg first. Okay, what will be the value of Vg? Vg will be plus VDD R2 over R1 plus R2. So can we calculate the value of Vg? Yeah, this is 1.8 volt. Yes, fine. So now we can apply some KVL and this voltage becomes Vg. Fine. So we can apply KVL and then it becomes Vg plus VGS plus ID into RS, that is equals to 0. And that will provide us VGS equals to Vg minus ID into RS. Okay, this is equation number 1. Now we have to apply the boundary conditions. Okay, we have to apply the conditions. First condition, put ID equals to 0. This will provide us VGS equals to minus plus VG. This is 2. And second condition, you have to put VGS equals to 0. And this will provide us ID equals to VG over RS. And VG you have already calculated, this is 1.82 volt. So I would like to draw one characteristics. I would take 2, 3, what is that scale? 8, 2, 4, 6, 8. I'm taking this one full scale. This I'm writing notations. One full scale equals to 2 volt. Equals to 2 volt. This one full scale equals to 2 volt. Okay, and I can put some marks over there. I can put some marks. Okay, let me do it. Fine. So this one full scale equals to twice 2 volt. Fine. Now 6. Again, I'm drawing a perpendicular line over there. Here, I'm drawing a perpendicular line, and this will provide us the value of I. This one. Okay, so here again on the vertical axis, this one full scale I'm considering as 2 milliampere. This is 2 milliampere, one full scale. Okay, so here I'm representing this axis via ID, and this is BGS, and this is okay BGS axis. Okay, so what was the value of BG from the first condition? If I apply first condition, that BGS, I got BGS equals to BG, and this is 1.82 volt. So 1.82 volts lies somewhere here because this is 2 volt. So 1.82 lies somewhere at this point, BG. Okay, second condition I got that ID equals to BG over RS. At BG equals to 1.82 over RS. What is the value of RS? 1.5 kilo ohm. 1.5 kilo ohm. And that from this point I got that ID equals to 1.21 milliampere. If you will calculate, this will be equals to 1.21 milliampere. Why 1.21 milliampere? So 1.21 milliampere lies somewhere like 1 point. This is 1 milliampere. 1.21 lies somewhere at this point. Okay. Do you have any difficulty? So with the application of two conditions, I got two different points, one on ID axis, another on PG axis. Now I can draw the straight line curve like 2, 4, 6, 8. This is IDSS. IDSS equals to 8 milliampere. And 2, 4. This is 4 point. This BP is 4 volt. So this is minus BP. If I draw the characteristics on this axis, then this characteristics will be like this. Transfer characteristics will be like this. Is there any problem? I don't think there is any problem. Okay, so now again let me use the ruler, and I can join these 2 points so that I can locate the cube. Okay, and so this intersection point will become the Q point. Okay, now I will draw the perpendicular lines on vertical axis and on horizontal axis. So now if we will calculate this value, I will put this scale, we'll put this scale on horizontal axis, and we'll calculate this value. This is around you can check it, this is to 1.8. This is around 1.8 volt. So on the horizontal axis we found that BGSQ equals to minus 1.8 volt. Okay, and if we check the vertical axis, so if we check on vertical axis, then it is around 1, 2, 2. This is around ID equals to 2.4 milliampere. Do you feel any problem in this whole exercise? That yeah, this is very easy and interesting as well. Utilizing two conditions, by utilizing two different conditions, we located the BGSQ and ID using, and we have drawn the transfer characteristics and located the Q point. Now directly we can find this BGSQ and ID. Now I can put this value of ID, and I can apply KVL equation at the output loop. That will become minus 16 plus ID into 2.4 into 10 raised to the power 3 plus BDS plus ID into 1.5 into 10 raised to the power 3 kilo. I can put the value of this ID cube from this point. I can put this value of ID and I can calculate the value of VDS. So we have calculated ID cube, VGS cube, and this is what is that? Next point. This is BDS. BDS. We have calculated BDS. No. Okay, BG. Three voltages we have calculated. Now we have to calculate BD. Okay. So how we can calculate? How can we calculate the BD? We know that VDS equals to VD minus VS. What is the value of VS? Can you please tell me? Please tell me the value of VS. What is the value of VS?
Sir, ID into RS.
Yes, exactly. So it will become BD minus ID into RS. Okay, so we have kept this value ID here, RS, and we already know the value of BDS from this equation. This will provide us BDS. Okay, and we can calculate the value of BD. So this BD is calculated. Now we have to calculate BDS. BDS already calculated. Okay, BG already calculated. What is the value of BDG? If we want to calculate BDG equals to, then it is BD minus BG. BG we know, BD we know, we can calculate BDG. Now tell me if there is any difficulty in mathematical.
Sir,
Yes,
in exam also we must draw with using scale, sir.
yes, exactly.
But the characteristics are not exactly, no, sir.
Who said that characteristics are not exactly same? You can use that compass.
Okay, sir.
You have this point, you have this point, then you can use compass. Approximately similar kind of value you will get. Okay.
Okay, sir.
Next kind of configuration, that is common gate configuration. Common gate configuration. What is that common gate configuration? So let me talk. I think you know the common gate configuration. Okay, and here this is one resistance we are utilizing. This gate is common and grounded, so that's why this is called common gate. This is plus minus VDD. This is RD. This is RS minus plus VSS, and this is gate terminal. This is source. This is drain, and this is gate. And similarly, we can go for that plus minus. This is BGS plus minus. This is BTS. And here this loop will contain current ID, this current will be IS, and this current will be IG equals to 0. And first condition, that is IG equals to 0, that will lead to provide us ID equals to IS. This is fine. So now we can apply KVL on the input loop, and that will provide us plus BSS minus IDRS, okay, minus VGS equals to 0. So that will provide us VGS equals to BSS minus IDRS. This is equation number 1. That we got, this is equation number 1. Is there any problem? I don't think there is any problem. Okay, so what we can do, again we can apply two conditions. First condition is, now we can apply two conditions. First condition that we can apply, that ID equals to 0, and that will provide us, we can put this in equation number 1, and that will provide us VGS equals to VSS. Okay, this is equation number 2. Second condition, we will apply that VGS equals to 0, and that will provide us ID equals to VSS over RS. That is equation number 3. Fine. Again, we can draw the transfer characteristics. We can put these conditions, and we can locate the Q point. And you know everything. How we can locate the Q point. I am drawing. Now I am drawing freely. Okay, you have to use scale. I am just drawing it freely just to save the time. And already all the things you know well. Fine. How to draw and how to make it perfect. Fine. So VGS equals to VSS. VSS is positive. So suppose VSS is there. Okay. Second condition, ID equals to VSS over RS. VSS over RS. Fine. And already you know that IDSS is given to you. IDSS is given to you. IDSS and PP. These both terms are given to you in the numerical problem. IDSS and PP. Okay. So here we can join the characteristics like that, and finally we got 2 points, and we can join these 2 points, and we can locate the Q point by using a straight line. Fine. And this will be the Q point. Q point. Okay, and here again we can draw a perpendicular on the vertical horizontal axis and vertical axis. This will become VGSQ and this will become IDQ. I don't think there is any problem. And here we can calculate VGSQ and IDQ. Fine, from above conditions. Fine. Now we can do one thing, like we can apply KVL in the output loop, and that KVL will become like plus VSS minus IDRS minus VDS minus IDRD plus VDD equals to 0. Everything you know, ID, VSS, VDD, everything you know, you have to calculate. This will provide us VDS. Fine. So let me solve one numerical so that you can understand it in easy manner. So you have one numerical. Tell me.
Common gate.
Common gate. Why?
So, from the gate side, yeah. Yes, sir. Now it is. So because both.
Yes, gate is common between drain and source.
Yes, sir.
Brilliant. Good. Okay. So now we can solve this and we can apply one KVL. This question is going to be very interesting for you guys. So keep note of this question. This is very easy. ID, this is IS, and you know that ID equals to 0. Since ID equals to 0, so it will provide us ID equals to IS. Right. So here, this is very important. Now we can apply the KVL in the input loop, and it will provide us plus VGS plus ID into RS equals to 0. So VGS is directly equals to ID into RS. You see the common gate configuration, one voltage was applied at the source terminal in previous configuration. One voltage is applied at the source configuration, source terminal, but here the source terminal is also grounded. This is very important. So that's why we apply conditions over here. So conditions will provide us, like first condition will provide us ID equals to 0 and this will provide us BGS equals to 0 volt. Second condition, we will apply BGS equals to 0, and this will provide us ID equals to 0. Now, this is very huge problem. This is very big problem. I hope you understood the problem. What is that problem? Do you understand this?
Yes, sir.
What is that?
Sir,
Yes, exactly. Brilliant, brilliant enough. This we are getting only 1 point. Okay, and if we are having this IDSS, this is 12 milliampere, and this BP this is around minus 6 volt. So if we draw these characteristics, so we are having only 1 point. This by both conditions, single point, and we cannot locate. So we cannot locate the Q point. This is the main problem here. We cannot locate the Q point. So what can be the procedure? For location of the Q point, for finding the location of the Q point, we can assume any value of ID. This point is very important. If we are stuck in this problem that we cannot locate the Q point just because of zero origin, these both points are situated stuck at the origin, and in that case we cannot locate the Q point, and that in this case we can go for that assume any value of ID. Suppose. So generally I'm giving you a hint that if you will just want to assume any value of ID, you can assume this is ID approximately equals to IDSS by 2 or ID approximately IDSS by 4. Any value you can assume. Okay, suppose I am assuming this IDSS by 2, 6 milliampere. I assume this. Okay, so if I assume this, so I can put this value. If I assume let ID equals to 6 milliampere. So from equation 1, we can find VGS equals to 6 into RS. And what is that value RS? 680 ohm. So VGS can be found like that. This is into power minus 3. So this will be, what can be the value of this VGS? Can you calculate? This is around minus 4.08 volt.
4.08.
This is minus 4.08 volt. Okay, so let me draw one line here, and this is 4. This I'm dividing is 3 and 4, 5. This point will be somewhere here, 4.08. So I'm drawing another perpendicular line. So I located some point here. So this is the procedure that I have drawn second point. 1 point I got that on origin. Second point I have drawn using my assumptions. Okay, now I am having 2 points, and then I can utilize the ruler or and finally I can draw the characteristics like that. This is load line. This is technically known as load line. Do you know? DC load line. Keep this in mind. Okay. And now this intersection on the transfer characteristics will be known as Q point. Okay, so this is Q point now. Okay, now I can sketch the perpendiculars on the horizontal and vertical axis. So this will be the actual IDQ, and this will be actual VGSQ. And using graphical method, I can calculate IDQ. This is around this is 12.6, and this is if I divide it in 3 portions. So this will be around something like mhm. If you will calculate using scale, so this will be around 4 milliampere, or exact value. This is if you will be using calculator. Oh, that scale ruler. In that case, it will be 3.8 milliampere, and PGSQ. You will find that PGSQ. This value is around 643. This will be around 3 or somewhere at minus, exactly it will be 2.6 volt. Okay, if you will be using rulers, then it will be like that. Okay, fine. I think this is very easy. Now you can put the value of ID Q, and you can apply one KVL equation in the output loop. Now it will be minus 12 plus ID into 1.5 into 10 raised to the power 3 plus BDS plus 680 into 10 raised 680 into ID, and equals to 0. Put the value of ID and find the value of BDS. I don't think there is any problem. Okay, now you have to calculate other parameters, like in the starting I forgot to write what you have to determine, and you have to determine over here. This is the first point, like BGSQ, IDQ, BD, BG, BS, and BDS. These are the parameters you have to determine. So you found this BGSQ, IDQ, and what is the value of BG? 0 volt. Okay, the value of BD. What is the? How can you find out the value of BD? Let me explain. First, we will try to find out this BDS you found. Okay, so from this BDS, you can write it like BD minus BS. What is the value of BS? What is the value of BS?
IS 6 to 680.
ID into RS.
ID
Yes,
into
yes.
RS.
So from this point, you can calculate BD. So BD you have calculated. Now BS, ID into RS, BDS you have calculated from this point, and BDS you already know. Do you know any? Do you think there is any problem?
No, sir.
This
No,
is
sir.
very easy and interesting as well. So last time I left this part of graphical representation, so it was very interesting as well. So I have repeated. Okay, now some other special cases are there. Like we had categorized this biasing for JFET. You have studied these four biasing. Now you have to go for RD equals to 0 and BGSQ equals to 0. Okay, you have to check out these two biasing by yourself. Now this fixed bias for depletion type and potential divider bias for depletion type, feedback configuration for enhancement, and potential divider for enhancement. These six biasing you will check it out by yourself. I told you each and everything. Okay, so your question is, study all kind of biasing in JFET and depletion type MOSFET and enhancement type MOSFET. So this is the question for you guys. You have to check it out by yourself. Fine. So this is end of this unit for you guys. This is the last. This was the last topic of this third unit, and one thing is remaining. That is symbols. Like JFAT symbol, you know. Do you know the symbol for that enhancement type or depletion type MOSFET?
No, sir.
Okay.
No, sir.
Depletion type MOSFET. Enhancement type MOSFET. Okay, and you can draw the symbols like for N channel. There are two symbols, two ways in which you can draw the symbols. This or this, similar. This is for N channel depletion type MOSFET, and for P channel, sorry, this is for P channel. Arrow is outside, so this is for P channel. For N channel MOSFET, arrow is inside. Okay, either this or this is PSS, this is PSS. This is N channel depletion type. Arrow is inside for N channel, arrow is outside for P channel. Fine. This is for depletion type. Now for enhancement type MOSFET. VSS. This is drain, this is source, this is gate. Drain, source, this is gate. Okay, this is drain, this is source, this is gate. This is a P channel. I think you are able to locate the differences between enhancement and depletion type MOSFET symbols. This is PSS. Drain, source, gate. And this is enhancement type MOSFET. So this is the only difference for the symbolic representation of enhancement type. This layer is separated view, is having separated view, and this layer is having continuous view. Okay, so this is the only difference. So this is the end of third unit. Now, if there is any problem in the third unit, you can share with me and you can find the solutions. Any doubt till now? ऐसा नहीं है कि आपको रटना पड़ेगा कहीं भी या रिमेम्बर करना पड़ेगा, ऐसा कुछ नहीं है. सब चीज़ें एकदम बेसिक इलेक्ट्रॉनिक्स, इलेक्ट्रिकल, केवीएल, केसीएल के बेस पे आपका सॉल्व हो गया है. जहाँ थियोरेटिकल डाउट की जरूरत था वहाँ मैंने आपको कॉन्सेप्ट बताया, उसमें अलग से टाइम आप अपना वेस्ट ना करें, ये मेरा सजेशन रहेगा. क्योंकि और आप डेली बेसिस पे रिवीजन करें, दैट विल बी वेरी बेस्ट फॉर यू. Otherwise, you will be in trouble in the last. Not for this as well. नेक्स्ट सेमेस्टर में आपको एक सब्जेक्ट और टेकल करूंगा मैं, सेमीकंडक्टर डिवाइसेस। आपने अगर बेसिक इलेक्ट्रॉनिक्स सही से नहीं पढ़ा होगा, then in that case you will be in trouble. The similar subject I am handling. Okay, so keep note of everything related to this subject, basic electronics. Fine. Now, small signal model. Okay. One small topic is remaining for on this third unit. That is small signal model of FET. Actually, H parameters. Have you studied H parameters in networks? Hybrid parameters.
No.
Actually, this topic is very much like parameters. Once you will finish the hybrid parameters in networks, network theorem you have finished. Have you finished the network theorem?
No, sir.
Okay, you are still working on network theorems. So once you will finish that network theorem, part of network theorem, that in that case it will be very easy to understand this small signal model. So in this case, H parameter, there is one term H parameter. Using H parameter you can draw. Here, okay, AC analysis. AC analysis, small signal model. This is AC equivalent circuit. So if you have the knowledge of H parameters, you do not have to keep this thing in your brain forever. Okay, let me draw it in a short way so that you just keep this circuit in your brain. Whenever you will finish the network theorems, in that case, it will be very easy to understand about this circuit. BGS. And this is GMBGS. GMBGS. This current is ID. So this is AC equivalent circuit, small signal model. If somebody says you draw the small signal model of MOSFET, so this will be the small signal model. This is the current. This is voltage dependent current source. This is gate to source voltage. This is RD. Okay, and here you can apply load resistance. This is output. This is input. Fine. This is gate terminal. This is drain terminal, and this is source terminal. Fine. So this is small signal model, and here some parameters are there. This is GM. This is transconductance. Okay. So there are three terms which are very important to understand. First term is ID equals to GM PGS. Okay, this is drain current in terms of transconductance. Transconductance is reverse to the impedance. Impedance is voltage upon current. Transconductance is current upon voltage. Okay, this is transconductance, and another term is what is the formula for GM? You can calculate GM by using GM equals to del ID over del BGS. Okay, and what is the value of ID? ID you will put ID SS 1 minus BGS over BP whole square. You put this value of ID over here and differentiate it. Once you will differentiate it, you will find the value of GM. This is 2 IDSS upon mod of BP, and here 1 minus BGS over BP. This formula you will get for transconductance. Once you will differentiate this equation of current, Shockley's equation, by putting this in this formula, equation number 2, you will find GM like that. Okay, and this is the magnitude of transconductance. This is GM naught. This is called maximum value, 2 IDSS over PP. Fine, and this term is similar. So you can solve the numerical based on this transconductance. Fine, and other parameters are similarly you can write RD. Another parameter is RD. Drain resistance. This is del BD over del ID. BD is drain voltage and ID is drain current. And you can calculate everything related to this. Another term is mu. Another term is mu equals to GM into RD. Okay, so these are three formulas. You would have to keep these formulas in your brain, and you can find this is mu is the GM into RD. And what is the value of GM? GM, you can check it out. This is ID over BGS into RD. So ID into RD, this is the voltage. Fine. This is drain voltage and this is gate voltage. So this is gain. Voltage gain. Mu is voltage gain. Okay, these are three parameters. This is drain resistance. Okay, this is voltage gain and this is transconductance. Three parameters you have to calculate. Fine. So you try to solve numericals related to this small signal analysis, then it will be very easy for you. So goodbye for today. We'll meet on the next lecture.
Thank you, sir.
Thank you, sir.